Okay, welcome everybody. So this video I'm going to talk about heat. I'm going to introduce the idea of heat energy, chemical energy, phase changes, and how energy is involved in phase changes. So the first thing you really need to be able to understand and define is heat energy. And heat energy, it is a form of energy that can be transferred between objects. And generally it'll be transformed from a hot object to a cold object or a cooler object. So if I have an object that's at 80 degrees Celsius and I place it in contact with an object that is 40 degrees Celsius, well, there's going to be a heat transfer. And so this one is going to get cooler and this one's going to get warmer. And depending on how much of each object I have, and if it's the same object or not, they're going to meet somewhere in the middle. So I don't know where they're going to meet. That's what we're going to do next. In the next video we'll talk about, well, where do they meet? What's the final temperature of the two objects? Also, you can think of heat energy as a kind of kinetic energy. And so when I think of this as a kind of kinetic energy, because really, if you have a hot object, that hot object, the particles are moving faster. And you may remember from your previous science courses, or maybe not, kinetic energy is talking about how objects move, or how particles move. And so the faster that you move, that means that you have more energy. Now, you also can have something called chemical energy. And chemical energy, this is energy changes during a chemical reaction, or during a chemical change. And so whenever you have a chemical change, you have bonds between the atoms that are broken and bonds that are formed. And when a bond's broken, there's energy absorbed. And when bonds are formed, energy is released. And so, when you have a chemical reaction, you have to see overall, well, the bonds broken compared to the bonds formed. Is energy released or is energy absorbed overall in the chemical reaction? And we'll talk more about that in a little bit. Now, in all chemical and physical changes, there's the law of conservation of energy. And this says that, the energy of the universe is constant, meaning it doesn't change. You can transfer energy. So you can transfer energy, but cannot create or destroy it. And so when we transfer energy, we think about the two main types of energy and how we would transfer between them. So kinetic energy, this could be heat energy, for example. And potential energy, this could be chemical energy, for example. And in a chemical reaction, we can transfer energy between heat energy and chemical energy. So, for example, if I have a compound where I have something like the natural gas that we used, and I react it with the oxygen in the air, well, it'll form CO2 and H2O. But also, it produces fire. It generates heat. So we took this chemical energy in this case, and as it formed into the products, we get an overall shift to where we're generating heat. So heat was given off in this case. You know some physics examples too that I can do in a different color here. So some physics examples where you have an object like a pendulum, and this pendulum can swing back and forth, and so when it's moving it has kinetic energy, but when it's stopped it has potential energy. If you don't know what a pendulum is, ask me tomorrow. I can do a demonstration for you with a pendulum. Now, we're really focused, though, on chemical reactions. We want to look at chemical reactions. We want to see, how energy is changing in a chemical reaction. And so you could have one situation. The first type of situation is where energy is released from the system. And so here, what happens is you have some kind of reaction. We go back to our natural gas reaction. And what we'll notice about this, and you did this in the lab, you lit this on fire, and then heat was being given off. You were able to heat up water with this. You were able to bend glass with this. Well, this will generate heat, and they'll show this heat will be given off. They call this exothermic. This is the release of heat, the exiting of heat from the system. Where does it go? Well, it goes to the surroundings. So it's released by the chemical system, and it enters the surroundings. And because it's entering the surroundings, and you are the surroundings, this will feel hot. Then you have, situation 2, where energy is absorbed by the system. And this would be something like, there's a few reactions that do this. You can dissolve some substances and they'll feel cold. Like, for example, if I take some KNO3, it's a salt. If I put this into water, it'll form from solid to aqueous. And this actually will absorb heat, so we would put the heat on the left side. And so now in this case, this would feel cold. They call this endothermic. So heat is entering the system, heat is absorbed. So we're going to go back to this idea again and again. We're going to talk about endothermic, we're going to talk about exothermic. We're going to talk about the idea of heat transfer. We're going to talk about the idea of energy transfer. We're always going to come back to law of conservation of energy. But let's talk a little bit about temperature. Temperature has a very distinct definition. You need to memorize this definition. It is a measure of the average kinetic energy of a substance. There are 3 temperature scales. There is the Celsius scale, there is the Kelvin scale, and there is the Fahrenheit scale. Kelvin does not have a degree sign. Celsius and Fahrenheit do. If I want to change from Celsius to Kelvin, the equation is Kelvin equals degrees Celsius plus 273. And if I want to change to Fahrenheit, I can do that from Celsius, and it is degrees Fahrenheit equals 1.8 times degrees Celsius plus 32. These 2 are the ones that are used in science. Fahrenheit is used here in the United States for weather, some other countries for weather, but by and large the world uses Celsius. Now, let's talk about, we're going to come back to temperature again and again, especially when we start looking at heating curves, especially when we start looking at heat transfer. because we're going to see what the final temperature is. But let's look at what happens, what happens if I start putting energy into a substance? Well, let's say I start at the solid. So if I had a block of ice, we had ice here at -20. Well, ice melts at 0 degrees. So before we can start melting it, that ice starts to heat up. So we need to heat up the ice. So the temperature will increase. As the temperature increases, since temperature is a measure of the average kinetic energy, the kinetic energy of the particles will increase. That means that they'll move faster. Now, as they move faster, they will reach a point at 0 degrees Celsius in which they will undergo melting. And at this point here, there will be no temperature change. So now there's no kinetic energy change because there's no temperature change. Instead, what we have is we have attractive forces breaking. And as those attractive forces break, the potential energy will increase. Remember, breaking bonds increases the energy. You need to absorb energy to break a bond. Now, once we melt, we'll form a liquid. And the same process happens at a liquid. From 0 up to 100 degrees Celsius for water, we're going to have a temperature increase. In fact, I can take this statement right here, and I can copy it, and I can paste it right here, and put it right here, because it's going to be identical. And once I reach 100, well, then the liquid starts to boil. It starts to vaporize. And now the same exact thing happened with melting, except now it's vaporizing. So now what's going to happen is if we go back here, I can just take this part right here, and I can copy it, and I can paste it right over here. There's no temperature change again, because now we're again breaking forces. And once I vaporize, well, I'll form a gas. And guess what? Yeah, that's right. I'm going to have the same thing I had with a liquid. Copy that and paste it right here. Whenever you have a phase change, you have the same type of thing going on, potential energy increasing. Whenever you have a phase being heated, you have kinetic energy going up. So now, how does this look graphically? Because that's really important. You should be able to see and look at this graphically. Well, let's look at a heating curve, what we just did if I heat up a substance. Well, we can graph temperature. We can graph temperature over time. When you have the solid and you're heating it, we saw that the temperature went up. So this would be where my solid was getting warmer. But we saw that when you melted, you were breaking the forces. So the temperature didn't go up. This would be melting. With the liquid, again, you were getting it to go faster. And when you vaporized, well, now we're going even longer here. Again, we're breaking the bonds. There's no change in temperature. And once you vaporize, you form a gas. With the solid, the liquid, and the gas, you have kinetic energy increasing. And with the phase changes, you have potential energy increasing, while kinetic energy stays the same. Now, I did something kind of interesting here, and I did it on purpose. If we look at the melting phase line and we look at the vaporizing phase, I purposely made this one longer than melting. And so I want you to think about that, because tomorrow, when we go over this and we talk about the phase changes, I want to really discuss with you, why is that longer? That's really important to understand. They ask about this now a lot, and I also want you to understand it because I think it's interesting. So what I'd like you to do on your own is try and do a cooling curve. Now, before we do that, and before I stop this, is this exo or endo? So what do you think, exo or endo? So these are some thought questions for you. Is this exo or endo? Why is the vaporization longer? And can you draw a cooling curve here? We'll discuss this tomorrow, and then we'll fill in the notes too. All right, thanks so much.